So in this segment, we'll take a look at the problem of signal detection, which is a fundamental problem in statistics and a particularly relevant problem to many medical applications, especially many medical software applications. So the history of signal detection comes from radar, and think here about World War II. You have this screen here, that's your radar screen, and you see this blip here appear on your screen. And so the question you have to ask yourself if you're running the defense of Britain during World War II is this a plane or is this noise? And if this is a plane, you have to ask to send a plane up to intercept the enemy plane so you don't get bombed. And if it's not a plane, you sit tight and you say, okay, that's just noise, we do nothing. The problem fundamentally here is what happens if you make a mistake. If this is in fact a plane and you choose to ignore it, you may get in trouble, you may get bombed. And if this is not a plane and you send something up to intercept it and they find nothing, you've just wasted valuable fuel, you have tired pilots, you add wear and tear to your planes and all kinds of other issues. So the fundamental trade-off is the cost of action when it is not needed versus the cost of inaction when in fact action were needed. So this is a trade-off in all of signal detection. What happens, what kind of mistake can we afford to make? So if you're in a situation here where you have lots of planes and lots of pilots and infinite fuel, then the cost of action is low and the cost of inaction is high. You don't want to be bombed, you have lots of planes, you're always going to send somebody up no matter what. Versus if you're in a situation where you have very limited fuel and you say, okay, we'll take the odd hit occasionally because we have to preserve our planes for those times we're absolutely certain there's a plane coming. So that's the fundamental issue in all of detection theory. So let's look at it a little bit more mathematically. And the case of event detection asks the question, really the question we want to know is, did something happen? Is there a plane there? So let's set this up mathematically in a little bit more of a medical context. Is there evidence of cancer in this mammogram? So a mammogram is used commonly to screen women for breast cancer. We see something. Is this cancer? Is this not cancer? That is the question we want to ask. So here's the mathematical setup. We have a function f of the measurements x. X is the mammogram. M is some algorithm that produces some estimate base of the mammogram. If f of x is small, we say that nothing has happened. There's no cancer. If f of x is large, we have an event. For example, we have cancer, an enemy plane, what have you. And what this boils down to is setting or estimating a threshold t such that if f of x of t, we have the event. Otherwise, we say we do not have an event. So if f of x is greater than t, we call that event a positive. Our algorithm says we have something. It's not good news necessarily that you have cancer, but that's what a positive cancer test means. It means there's cancer present. And if f of x is less than t, we call that event a negative. We do not have cancer. So let's look at it a little bit more again, and let's think about it a little bit more graphically here. So we have four kinds of situations. We have our algorithm says yes or no, and the event, the true value, which is unknown, of course, to us, is yes or no. And we end up in this 2x2 table. We have true, positive, false, negative, false, positive, and true, negative. Those are the four things. For you to remember what those things mean, the word positive refers to what the algorithm said, and the word true or false refers to whether the algorithm was correct. So a true positive means we had a cancer and we called it correctly. A true negative, we did not have cancer, we called it correctly. A false positive, we said there is cancer, but we were wrong, and the same applies to false negative. So let's dig in a little bit more. If f of x is greater than t, we have a positive result. Otherwise, we have a negative result. Our result can be true, correct, or false. And false positive, just to reiterate, means that we said something happened, but in fact it did not. And the problem ultimately is a trade-off between false positives and false negatives. So these are the bad things, the thing in red here, and our trade-off between those two things. A false positive, we said there's an enemy plane and there's no plane. A false negative, we said there's no plane, but in fact there is a plane. Those are the things we try to avoid. The other terms you will hear in this discussion are these concepts of sensitivity versus specificity. Sensitivity, a high sensitivity algorithm says we do not want to miss any cancers. So we want to minimize false negatives, situations where we said there is no cancer when in fact there was cancer. Remember, negative means we said there's no cancer and we were wrong, it was false. So the formula for sensitivity is this fraction between true positives and all positives. True positive means we said there was cancer and there was, and then false negative, there was actually cancer, but we failed to detect. So what fraction of cancers do we detect? That is sensitivity. The other parameter, the thing we trade off with, is specificity, which says that when we give a cancer diagnosis, in fact, we are correct that it is cancer. So this is the goal here is to minimize false positives. And the formula, again, is the sum of is a fraction of true negatives when we said there was no cancer and we were correct, over true negatives plus false positives when we were wrong. We said there was no cancer, where there was cancer, but we were in fact wrong. The key is trivially easy to maximize each of these things separately. We can call everything cancer, and we have high sensitivity, no big deal. We can call nothing cancer, we have high specificity. So the game in detection theory is to figure out the optimal trade-off between sensitivity and specificity. So if you hear somebody say, our algorithm has 80% sensitivity, you say, thank you very much, I can get you 100% sensitivity. The question is, what specificity do you have at 80% sensitivity? And unless you've specified both, the answer is meaningless, because I can get you 100% sensitivity or 100% specificity, provided I'm not constrained by the other parameter. The way we think about that now is we're looking for f of x greater than t, and our goal is to set t to be that optimal trade-off between sensitivity and specificity. So the way we think about this is often graphically, and this is what's called the receiver operator characteristic curves. This is the sound of radar you're hearing, when we plot what's called 1 minus specificity, the false alarm rate, versus sensitivity. Where you want to be is here. You want perfect specificity. Remember, this is 1 minus specificity, so this is 1, and perfect sensitivity. We can never have that in the real world. So what happens is that we plot the performance of our detector. Remember, our detector is f of x greater than t as we vary this value t. If we set t very low, we have perfect sensitivity. We don't miss anything, but we'll have lousy specificity. If we set t very high, we end up at the opposite end. We have excellent specificity, but we have lousy sensitivity. And if we vary t, we end up with this curve. This is what's called the receiver operating characteristic curve, and that shows us the relative, the pairing of sensitivity and specificity. And the way we set t is based on the relative cost of false alarms versus failure to detect. So if we are doing a detector, and the goal is of the algorithm is to detect bombs in people boarding a plane, because we are sort of worried about terrorist attacks, we're going to optimize for sensitivity. We're going to set t very low, and we're going to take all the hits on specificity. And this is what in fact happens. That's why every single suitcase gets open in a plane when you're boarding a plane, because you're optimizing for sensitivity. On the other hand, often in the legal system, you've heard the expression that better 1,000 guilty go free than one innocent man goes to jail. We will set our threshold very high because we're really optimizing for specificity there, and we'll be on the other end of the spectrum. Another measure that you will see is what's called the area under the curve. This is the area under this curve. Remember, the perfect curve would go up vertically here and horizontally across, and this would have an area of 1. The closer you get to 1, the better you are, and this is a measure of performance of an algorithm. And you'll see people specifying areas under the curve. This kind of thing we pose it here in the context of detection, but it's the same as when you're doing binary classification. Okay, it's the same idea. To sort of discuss this, to give you a second description of this is extracted from a segment from an interview from Dr. Nicholas Patrick from the FDA, and he'll state these things just to give you another view of the same problem.
Typically in an artificial intelligence, you have an output score that comes out of the algorithm. So for a case, you say it gives you a score on a 0 to 1 scale, with, say, 1 being higher, meaning it's more likely to be cancer. At some point, the company or the developer decides, you know what, I'm going to make a threshold at 0.75. So everything about 0.75 I'm going to call cancer. Everything below 0.75 I'm going to call not cancer. So that would give us this sensitivity, specificity, operating point of the device. But what we're interested in is that overall performance of the algorithm. And so what we can do is plot the sensitivity and false positive rate for all the different thresholds of that algorithm. And we can track that across the whole spectrum. So we can go from 0 to 1 in false positive rate, which subsequently goes from 0 to 1. So here's an example of a classifier. Typically, when we have a distribution, we have, again, this non-disease distribution and the disease distribution, and they overlap in some extent. So we're not going to get perfect separation between these two for most classifiers. So we have some overlap. If we separate those two out, again, put this threshold on there, we can get a single operating point. If we start and just sweep across the whole range, we can get the full ROC curve. And so this ROC curve tells us more about the fundamental properties of the algorithm and not for just one individual operating point.
And ROC curves is the right way to characterize a detection algorithm, because depending on your application, you understand the threshold separately. When it comes to comparing algorithms now, The ROC curve really measures the skill level of the user or technology and gives you a lot more information than just a single point on the curve. And it can be used to compare detection algorithms and binary classification and all of those things. Sometimes we're only interested in the performance for a specific range. For example, if it's an algorithm to detect, again, explosives in luggage on a plane, we're not really interested in the range below a sensitivity of like 99.9%, right? You could be doing better at sensitivity of 2%, but that's of no interest. In other cases, we want to see the whole range and compare over the whole range again. So we have a second clip from the interview with Dr. Patrick, who's going to talk to us a little bit more about this comparison thing.
So this is important because sometimes we have trade-offs in device performance where we have, say, a device A, which has a sensitivity specificity operating point of here, and a device B with a sensitivity specificity operating point here. And in this case, you can see that this device has higher sensitivity, but it also has lower specificity. So the question is that a good trade-off of performance? Is this operating point better than that operating point? Now, we could do something like utility analysis and try to determine what the value of a true positive, false positive, and so on. But another way of doing this is to actually look at the ROC curve. So are these two ROC curves the same or different? So in this case, the device B actually falls on a lower ROC curve, which gives us an indication that overall, this technology probably isn't as good as the technology for device A. Now, it's possible it could have fallen on a higher ROC curve, and it would have shown that that device was better. So again, this is a way to look at the technologies more of in a fundamental properties and try to determine which of these technologies are providing better information. Because in general, you can control the operating point. We can adjust these thresholds and operate anywhere along this curve that makes clinical sense.
So this concludes our discussion of signal detection, this brief introduction to signal detection. In the next 3 segments, we're going to take a look at math designed to evaluate clinical trials, and we'll talk about hypothesis testing and randomization. Thank you.